Welcome, everybody, and thank you for attending the AIAA Space Resources webinar. This webinar series, hosted monthly, is hosted by the AIAA Space Resources Technical Committee as an education and outreach effort to, get some of this information out amongst our community and amongst the general public. So my name is Jared Longfox. I am the chair of education and outreach for the AIAA Space Resources Technical Committee. And let's see, other logistics. Today we have Dr. Andrea Rajsic going to talk to us about impacts and seismology on the moon. I won't steal her thunder, but before I actually hand it over, I do want to say that, again, these talks are recorded and will be put on YouTube after. Towards the end of the presentation, I'll send a link to the page where they're hosted, so you guys can access that later. Keep an eye out over the next couple of days, and I'll get that uploaded. The Q&A. We do have Q&A, so at least on my screen, along the bottom right, if you don't see it right away, there should be a Q&A like speech bubble with a question mark in it. And if you don't see it, under the More tab, the three dots in the circle, you click that and Q&A will come up. You can punch your questions as we go through this in the Q&A, and we'll take them as we go, at the very end in the order received. I'm going to enable closed captioning. We are recording. I think I've said everything I've had to. So without further ado, Andrea, thanks for lending your time and expertise to this. Take it away.
Okay, I'll share my screen. Can you see my screen?
Looks great.
Okay. So yeah, thank you, Jared, for inviting me to give a talk. And so, as Jared mentioned, I work a lot with craters and cratering physics. And today, because of the nature of the talk, I'll talk about two projects that are related to the smallest craters that form on the moon. And so here we have a surface of the moon on the left and the surface of Callisto on the right. So two very different bodies. And basically across the whole solar system, craters are the most common geological process that happen on planetary surfaces. And what I care about is how do these craters form, and especially what we can learn from them about planetary surfaces. And at the larger sizes of craters, we can also learn things about planetary interiors by studying impact craters. And now we know that craters are everywhere, but in the past it wasn't really like that. So Galileo, for the first time, detected impact craters on the moon in the 17th century. But it was not until the 1930s that most astronomers believed that the moon's craters are actually just extinct volcanoes. And for some, it took until we literally landed on the moon in 1970s to really believe that these circles that we see on the moon are actually impact craters and not extinct volcanoes. And there are basically three reasons why scientists didn't want to believe that craters on the moon are actually of impact origin and not volcanic origin. And so the first reason is the abundance. So essentially, when you look at the moon, you really see a lot of craters. Literally, the whole surface of the moon is cratered. But on Earth, today, we have 194 confirmed impact structures on Earth, and these fireballs indicate where these impact structures are. And you can imagine that in 17th century, when Galileo proposed that these are impact craters on the moon and not volcanic craters, we knew of even less than 194 impact structures. So basically, by comparing geological processes on Earth, where we have many more volcanoes than we knew at the time, and very few impact craters that we knew at the time, people just like used analogy and were like, well, if there are more volcanoes on Earth, that means there are more volcanoes on the moon. Now we know that these are of impact origin and not volcanic. Another reason for another argument against impact cratering origin of craters on the moon was the sizes. So essentially, when you're on Earth, you can literally see some of the craters on the moon, but with your own eye or with telescopes. And so people were arguing that, oh my God, how big the size of the bodies would, like the asteroids that hit the moon, should be in order to form these huge circles that we can observe from the Earth. And so it wasn't until we started doing basically impact experiments like this one that we see on the slide, where we learned that it's not the impactor size that controls the size of the crater, but it's velocity of the impact. So essentially, a body that is 10 to 30 times smaller than the crater that it forms can form. So a very small body can form 10 to 30 times larger crater than it is because it moves at a very high speed. And the last argument was the circularity. So essentially, we know that asteroids hit the lunar surface at an oblique angle. So they don't impact it vertical, like they don't impact the lunar surface vertically, they actually impact at 45-degree angle. And so the argument was, well, if impacts happen at a certain angle, they should be oblique and not circular. And so it wasn't until we started doing detailed impact experiments, so started studying impact physics, that we learned that essentially at very shallow angles, we can still form circular craters. And what you see here on this slide is on x-axis is angle of impact. So from 90 degrees, so vertical to 0. So essentially just like impacting flatly into the target. And on y-axis is diameter ratio. So diameter ratio means diameter that was measured perpendicularly to the impact direction and in a line with the impact direction. And so the ratio between these two diameters, if it's 1, that means that the crater is circular. If it's less, if it's more than 1, that means that crater is oblique. And what you can see is essentially that for different impact velocities, basically until the very shallow angle, so much lower than 30 degrees, or around 15 degrees is when we start getting oblique craters. Essentially, if we have craters that impact lunar surface at an angle that is larger than 15, we will always get a circular crater. So studying impact physics, so angle of impact, velocities of impact, and actually observing the craters on the moon helped us confirm that impact cratering, it helped us confirm the impact cratering origin of craters on the moon. And today we know that we have also craters of different morphologies. So the moon is a great place to study the impact craters because it has the best preserved cratering record because it lacks other geological processes, right? On Earth, we have plate tectonics, we have atmosphere, we have water, all these components of Earth essentially erase the cratering record versus on the moon, we don't have any of this. So we have craters that are old and that are very well preserved. And what I'm showing here are 3 different distinct morphologies of impact craters that we observe on the moon. And from left to the right, they increase in diameter. So on the left is the simple bowl-shaped crater. We call this crater simple because they literally, as I said, bowl-shaped. So they are literally like a bowl, as you would imagine an asteroid hitting the surface of the moon and excavating a bowl. They have nicely raised rims, nice ejecta blankets, and bowl-shaped interiors. As you get larger in size, so basically this is Tycho, which has 85-kilometer diameter crater, you start getting more complex morphology of craters. And so we call these craters central peak complex craters, because as they get bigger, essentially you get this central peak forming in the middle of the crater. Then we have flat floors, and then we have terrace rims. So much different than the simple bowl-shaped crater. As you get even larger in size, so for example, as Schrödinger-sized craters, which we call actually peak ring impact basins, so at around 320 kilometers in size, this central peak, like as it forms, it overshoots the pre-impact surface and it splashes down and forms this mountain that we call a peak ring. So the distinction between the central peak and peak rings is that in central peaks, basically this uplift that happens, the uplift of the floor that happens essentially freezes, versus in peak rings, it just keeps going up, and when it falls down due to gravity, it forms the peak ring. So these are three very distinct morphologies. What we know also is that these morphologies also differ in not just the changes, not just in diameter, it's also in the depth of the crater. So essentially, until something like 15 kilometers in diameter here, we get increase in crater depth very smoothly. So as the crater as the crater diameter increases, the depth also increases. And then around 15 kilometers in diameter, we get a little kink in the and crater diameter still keeps rising, but crater depth doesn't change as much. And this is because essentially when you have the bowl, the bowl-shaped crater, the crater depth increases with increasing diameter, but as soon as you start uplifting the crater floor, the crater depth reduces. Like it is much, the ratio between the crater diameter and the crater depth is smaller. And so essentially, because we have these different sizes of craters, they excavate different depths of the moon, right? And the way they form and their sizes and their morphologies actually can tell us a lot about lunar history. So at the smaller sizes here on the right-hand side, so craters that are smaller than 15 kilometers in diameter, simple craters, can tell us a lot because they form on the surface on the moon and they excavate surface layers of the moon. They can tell us a lot about surface history and surface evolution of the moon. As we get to larger sizes, we also go back in time because these larger sizes formed in earlier history of the moon. So Tycho formed around 100 million years ago. This is just enlarged picture of the Tycho. This is not how we observe it at the moon. This is where it is, and this is just enlarged. So as we go as we start studying larger sizes, we essentially learn about the crustal evolution of the moon because a lot of the crustal properties of the moon control how these craters look like. And if we go at even larger sizes, so here I show the moon as seen by GRAIL, so the gravity mission on the moon, where the warmer colors are showing the thick crust of the moon, so up to 60 kilometers, and then colder colors are showing thinned crust of the moon. And so in this bluish green is actually shown the South Pole Aitken Basin, the largest basin on the moon, which is around 2,500 kilometers in size. And it formed at around 4.2, 4.3 billion years ago. So very early on in lunar evolution. And studying these largest basins can tell us a lot about thermal evolution. So essentially studying the size, morphology, progression of craters can tell us a lot about surface, crustal, and thermal evolution of the moon. And today, because this is more resources oriented and engineering oriented audience, I'll be talking about just these craters that help us to study surface evolution of the moon. And so the first research question that I ask is, can we relate regolith production on the moon to the surface age of the moon. And of course, that's important because we land there. So what is really regolith? Regolith is a layer of loose fragmented material that basically covers surfaces of all solid planetary bodies in the solar system, not just the moon, but also Mars. Here shown on the left-hand side is the robotic arm of InSight lander trying to scoop the regolith. And then on the right-hand side, we have the Bennu asteroid sampling, where all these regolith is flying around. So essentially, regolith covers all planetary bodies, and regolith is formed by continuous impact bombardment of these solid planetary surfaces. For the moon specifically, regolith, because it's formed by continuous impact bombardment of solid surfaces, regolith basically contains the information of the whole impact history of the moon. So when we bring back samples of regolith, the grains within the regolith will be shocked, will be melted. These shock and melting events have different ages, so they can tell us when this regolith was overturned, when this regolith got formed, how it evolved over time. But then on the other hand, where are we going to find these volatiles on the moon that we are going to the South Pole for? Well, we are going to find them in regolith, right? So essentially, the thickness of regolith is very important. We need to know how thick the regolith at the south on the moon and on the South Pole is in order to know how much resources we can find within the regolith. And so in the past, people, so this is like schematically description of how people studied regolith thickness on the moon. And so this is a schematic that shows the approach of Quaid and Oberbeck that was developed in the 60s, where essentially this is impactor, so my asteroid hitting a two-layer target. The top is regolith layer, the bottom is bedrock layer. And essentially, I told you how simple craters are bowl-shaped. Well, if there's some kind of difference in layering, they will not always be bowl-shaped. So in a situation where impact happens and it excavates only regolith layer, sure, the crater will be bowl-shaped. But in a situation where asteroid impacts the surface and excavates the regolith completely to this bedrock layer, we will get flat-floored craters. And in a third scenario where impact has enough energy or regolith layer is thin enough, we will excavate the whole regolith layer and penetrate into the bedrock and form concentric craters. And so what Quaid and Oberbeck did, they did a series of experiments, varying impact experiments, varying kind of the regolith bedrock layer structure. And they found a relationship between regolith thickness and the size of the outer and inner crater diameter. And so this is like approach that was developed in the 60s, and it was followed by many people since the 60s. But essentially, in 2018, over 1,000 numerical models using shock physics codes basically showed that these concentric craters here on the left and on the right can form not just because we impacted the bedrock or the stronger substrate. They can happen, these morphologies can occur simply due to some strength discontinuities within the regolith layer. So for example, imagine if you have a regolith and it overlays some stronger rock. However, within the regolith, you can have a melt sheet from a larger basin somewhere in the distance. And so basically your relationship between the outer and inner crater then does not imply the regolith thickness, it implies thickness of the regolith to the discontinuity within the regolith. And so because of that, I apply in my research the rocky ejecta approach, where essentially if the crater forms in Just in regolith, it will not have rocks. It will not excavate any kind of solid rocks around it. However, if the crater forms in regolith and excavates the stronger substrate or bedrock beneath it, it will have some rocks around it. And so this is what we call a rocky ejecta crater approach. And so in the last year, my student and me mapped around 346 craters on the moon in diameters between 10 and 240 meters in diameter. And we classified them according to the presence of rocks in the ejecta, as I just explained. And so here on the left-hand side, you can see a very small non-rocky ejecta crater. So you can see the very raised rims and nice ejecta blanket around it. However, no rocks are present, versus on the right-hand side is a slightly larger rocky ejecta crater where we have rocks visible within the crater bowl and around the crater in the ejecta. And so not only that we mapped these craters to like within the limited diameter, but we also focused on the very fresh looking craters. So what that means is, for example, this is the same rocky ejecta crater that I showed, but in the right corner of the image, you actually see a super, super degraded crater. So we limited our search across the moon on finding the craters that have very visible ejecta and very visibly raised rims. So this crater in the right corner essentially is very degraded. It doesn't have very visible crisp rim. It doesn't have visible ejecta around it, and it has a lot of infill. So even though we would, for example, within this range, 10 to 240, find craters like this, we would not account for them in our analysis. So 346 fresh craters. Some of them have rocks, some of them don't. And so on the moon, we have near and far side, and we have two distinct geological units, so mare and highlands. Maria is primarily on the near side, some is on the far side. Mare are those dark patches that you see on the moon, and then the highlands are older, heavily cratered materials, that heavily cratered terrains that are lighter in color when we look at the moon. And our search areas were we searched in 6 areas here shown as orange dots in the Maria and 7 in the far side. Here are 6, but this one here is like there are 2 dots very close in the Maria. One of them is actually in the highlands. And so we searched, so we found essentially 346 fresh, non-rocky and rocky ejecta craters in highlands and in Maria. And so how does that distribution look like? So this is just a histogram showing the frequency of craters that we mapped in Mare region. And in Mare, we mapped 147 craters. The total number of non-rocky ejecta craters is 70, and 77 are rocky ejecta craters. And here on this histogram, I show rocky ejecta craters in this purplish blue color, and non-rocky ejecta craters are shown in orange. And you can see the distribution basically with size. We have an overlapping region essentially here. So basically at around 25 to like 60 meters in diameter, we have an overlapping region where we find in different Mare regions, we can find both rocky and non-rocky ejecta craters. And then past this 60-meter diameter, we don't find any non-rocky ejecta craters. So all craters larger than 60 meters in diameter essentially have rocks within them and around them. In highlands, we mapped 199 craters where 118 are non-rocky ejecta craters and 81 are rocky ejecta craters. And when we look at the distribution in highlands, it's essentially like similar, where we have the overlapping region at around 30-ish meter in diameter, where we have And then this overlapping region goes until 110 meters. So between like 30-ish meters in diameter and 110 meters in diameter, in some regions of highlands, we find both non-rocky and rocky ejecta craters. But past 110 meters, we don't find any non-rocky ejecta craters. So every crater that we find that is larger than 110 meters in diameter contains rocks in the ejecta or within the crater bowl. But what does that tell us about thickness of regolith? So this is again a nice schematic showing how we can actually see the thickness of regolith from the crater diameter. So what we measured were crater diameters, and we want to see how much of the regolith those craters excavated. So this is a schematic showing the transient crater. So during crater formation, we have transient crater first, and then this transient crater collapses due to gravity. And at the third stage, we have the final crater. And so transient crater is essentially the stage in impact crater formation when we have the deepest crater, not the largest in diameter, but the deepest crater. So because during this stage, essentially when we have crater formation, some of the rocks are ejected, but some are pushed down by the shock wave. So the transient crater depth does not indicate fully how much of the material was excavated, because some of it was just pushed down by the shock wave. And from crater scalings and a lot of experiments and a lot of tests, we know that transient crater depth, that the excavation depth of the crater is related to the transient crater diameter. It's just 1/10 of the transient crater diameter. But for the final crater, because we have this slumping, we know that from scaling, we know that the final crater depth is larger than the final crater diameter is larger than the transient crater diameter, and it is essentially 0.84 of the final crater. So using these relations between transient crater and final crater and excavation depth, we can find that if we measure, like we did on the surface of the moon, sizes of craters, so their diameters, we can actually use this simple relation to find the excavation depth of the craters. And so that's what we did. We basically took our whole data set. We used all the kind of diameters of the craters that we measured, estimated the excavation depth. And what you're seeing here are two sets of data. So on the left-hand side, highlands, and on the right-hand side, the Maria. On the left-hand side, and these are like the violin plots that show logistic regression that we modeled in order to confirm what is the kind of regolith thickness on the moon. So as I was saying, like the largest non-rocky ejecta craters in Mare is 60 meters. And the largest non-rocky ejecta in highlands here it says 89, but it's not 89, it's 110 meters. So if we use these as an indicators for regolith thickness, this is very data point and very mapping limited kind of approach. So what we did is we used the statistically robust modeling approach, where we basically model a logistic regression on our data sets. So in the highlands, you can see non-rocky ejecta craters as blue and rocky ejecta craters as orange. And with the just approach using the largest non-rocky ejecta craters in the highlands, we would get regolith thickness that is 9.3 meters. But using logistical regression, where we have 50% probability of both craters being non-rocky or rocky, we get around 6 meter regolith thickness. So there's like a 3-meter difference in regolith thickness between two approaches. We adopt this value of 6 meters. On the other hand, when we look at the Mare distributions, where we show non-rocky ejecta craters in purple and then rocky ejecta craters in pink, we get that regolith thickness using the largest non-rocky ejecta crater is 5 meters versus using our logistic regression test, we get 4 meters. So only 1 meter difference. And I say only, but if you in the past digged a 1 meter of dirt, you would know that that's quite a lot. But what we see from here is that essentially we have 6-meter regolith thickness in highlands over our 7 different regions in the highlands, and then we have 4-meter regolith thickness in Mare. So these two geologically very distinct areas, Mare being younger, has 33% thinner regolith than the highlands. Another interesting point that you can see here is also that this difference between 9 and 6 and here 5 and 4 essentially shows how that highlands is much more geologically diverse terrain. And so I'll speed up a little because there's more to talk about, but essentially we confirmed our results by using the bootstrap sampling, where we sampled 1,000 rocky ejecta craters and 1,000 non-rocky ejecta craters within Mare and highlands. And what we get is that the mean thickness is around 4 meters in the highland, Maria, here shown in red, and in the highlands, it's around 6 meters, here shown in blue. What is important also to note using this test is that there are no overlapping uncertainties. So the dashed lines show the 95 percentile uncertainty, and there's no overlapping between them. So Mare and highlands are very distinct data sets. And so, as I was mentioning, one of the long-standing question in planetary science is like, is the depth age hypothesis. So does the regolith thickness on the moon increase with age? And so what I'm showing here is on the y-axis on the left, regolith thickness in meters. And then on the x-axis is age of the terrain. And on the right-hand axis, on the right-hand y-axis is the lunar chronology function. And so essentially what we did next is in blue triangles, we show our data, and in all the other colors, our data sets that we collected over the literature. So anything that was published on regolith thickness, from seismic measurements, Chang'e samples, different mapping approaches. And what you can see is essentially around 3.8 billion years ago, we have a strong drop in regolith thickness. So before 3.8 billion years ago, we have much higher cratering flux. And during that time, we have also the more production of the regolith, right? So it goes all the way up to 12 meters, and then it decreases to at around 3.8, it kind of stabilizes around 4 to 6 meter regolith thickness. And so, as I mentioned, we mapped our craters in 13 different regions in Mare and highlands. But as I showed here, we collected all the data from other sources, right? And so we now combine our data points with all these data points that we collected and construct basically a map of regolith thickness on the moon. Map is derived from inverse distance weighing, and it shows the regolith thickness on the near side and the far side. The importance of this map essentially is that it shows, first of all, the regolith thickness distributions on the moon, but second, it shows all the gaps that we all the areas of the moon where we don't have enough data. And so when we overlay the mare, you can essentially see that much thinner regolith is found in mare regions, and then it is beyond 6 meters around highlands. And so to conclude this part, we mapped 346 fresh non-rocky ejecta craters and rocky ejecta craters across previously not mapped regions in the highlands and mare on the moon. We modeled the probabilistic transition between regolith only and bedrock excavation using logistic regression with stratified bootstrap resampling. And our results from our statistical modeling results show that Mare has 33% thinner regolith than the highlands. By combining our measurements with all the published data sets, we kind of reassessed the depth age hypothesis at a global scale on the moon. And when we grouped these data sets according to the geological era, we find that there is a first order decrease in regolith thickness around 3.8 billion years ago. And when we integrate our new terrain scale estimates with existing measurements, we generated the first kind of global regolith thickness map of the moon. And so I'm going to skip now gears a little. And so on one hand, we can use these simple craters to study regolith thickness and regolith processes on the moon. But on the other hand, these small craters actually happen still happen on the moon. And we're going to the South Pole and we will place seismometers at the South Pole. And the next question that I ask in my research is how many impacts will be detectable at the South Pole seismic stations? And so we were at the moon in the past, right? We had Apollo Lunar Seismic Experiment Package. Here are locations of Apollo Seismic Experiment Package on the moon. And we have detected over 1,200 impacts happening on the moon at a time. Seismic detectability of impacts, here I show just illustratively, is a function of target properties, so the density of the target, of impactor properties, so how dense is the impactor, how fast is the impactor, and at what angle impact happens, and also the distance between where impact happened and the seismic station. So there's a lot of variables that control whether we can or not detect an impact. And in the past, as I mentioned, these seismic stations detected 1,200 impacts. We know that there are impacts because they have different seismic signature than the standard moonquake. However, we don't know where these impacts happened. For the only ones that we know where they happened are the artificial impacts on the moon. So here in the right-hand side corner, I showed the Saturn IV booster drop. And because we now have LROC images, we know exactly where these impacts happened and how big the crater they made. Because we know that the crater was made by the Saturn booster, we also know how big the density of the booster, the size of the booster, at the velocity at which it impacted lunar surface. So essentially, we have all these variables are known, right? We know how far it is from the seismometer. We know what is the impactor, what was the velocity of the impact, and we know how big the crater it formed. And so what I did in the past, so this is from 2021, I essentially just validated the ISIL 2D shock physics code, the code that is used to model crater formation. I validated it for seismic detections of artificial impacts. And so this was a super fun project where because ISIL is 2D axisymmetric, I had to represent the booster in different geometries, always maintaining the impact momentum. So always maintaining the mass of the booster. and the velocity of the booster. So different shapes and sizes, but mass is always the same. And how that looks like, so essentially this is um, um, pressure field taken from the ISIL simulations, where in these yellow dots are essentially my artificial seismometers, where I record the arrival of the pressure wave as it travels through the target. And because I place them at the equal distances, I know the distance and I know where the impact happened and I know at what time and how, and I know the amplitude of this pressure wave. So I have all these knowns. And so how we validated it is literally I used my artificial seismometers, recorded the P wave peak amplitudes, and here I show how P wave peak amplitudes decay with distance from the impact point. And essentially, the triangles show results from my simulations, and then the little squares show the results from Apollo lunar seismic experiment package. So the actual like seismic measurements from Apollo. And using, plotting this, we basically find the function that shows how P wave peak amplitudes decays with the distance from the impact point. And so another important thing, as I mentioned, is that we know that the properties of the target will attenuate the seismic and the shock wave differently. So another important point is that these plots here, these four plots show how the pressure amplitudes look in the non-porous target and then with increasing porosity from 25 to 65. So obviously at the same distance, the amplitude of the pressure wave will be different in different target analogies. And so what we do, but um, while we know that there's like that we have validated our code against Apollo seismic boosters, we know that the pressure wave will be different in different targets. Now we need to ask a question of how big are these craters that are happening right now at the moon? And here I show craters that formed on the moon between 2009 and 2015. And all these craters have diameters between 1 and 50 meters. Because we know their diameters, we know their excavation depths, and their excavation depths are from 0.084 to 4 meters. So essentially, because the regolith thickness on the moon, as we measured it in the previous work, is around like the thinnest what we found is like around 4 meters. That means that all these craters form in regolith. So regolith properties will very much control, on one hand, the detectability of these impacts, and on the other hand, we have these sizes, so we can actually estimate the impact momentum. Just using simple scaling laws, we can find how big the impactors that made these craters are. And so because we know the impact momentum, we can use our little scaling laws and find the ranges of seismic moment that these newly formed impacts will produce on the moon. And so that's shown here with the blue lines. I'm speeding up a little because we're getting close to the end. But so knowing the sizes of craters, knowing the relationship between seismic moment and impact momentum, we can see how big the seismic moment will be produced by these impacts. But another awesome thing that we can do is we can see how large the P wave peak amplitudes will be. Because we have all these relationships for P wave peak amplitude decay with distance. And so here I show 10-meter crater as a solid line, 10-meter crater diameter, and as a dashed line, 10-meter crater that is formed in regolith. So solid line is crater forming in bedrock, dashed line is crater forming in regolith. And you can see that at the same distance, we will have 3 orders of magnitude different P wave peak amplitude between regolith and bedrock. And then in the dashed dotted line, I showed the 30-meter crater forming in regolith. So essentially, we have these two sizes and these two materials for the same size. And if you look at this plot, you essentially can see that for these craters that are forming in regolith, the difference is essentially the exponent in the equation is the same, and the difference is only in coefficient. So I can use the power law and fit this function across different sizes on the moon. So from 1 meter, shown as a solid blue line, to 50 meters in diameter. And I can essentially find what will be PV peak amplitudes at different distances. And when I plot the LATAM results, they essentially lay on this 30-meter line. So to conclude, this part is we combined the crater scaling relationships, numerical modeling, and Apollo Lunar Seismic Experiment Package seismic observations to estimate the seismic signatures of small lunar impacts at the lunar South Pole. Our results essentially constrain the impact momentum of currently forming impacts on the moon, seismic moment, and the decay of PV peak amplitudes with the source receiver distance from craters 1 to 50 meters in diameter. And incorporating, so essentially, because this is not done work, what we need to know is we need to understand the instrument noise and the receiver properties in order to actually say how many of these impacts and at what distances we can actually detect them. And that's it.
Very cool, Andrea. Thank you so much for sharing this with us.
It was a little fast.
No, it's fine. And people can always reach out with questions. Your email is on this slide. Okay, well, I guess we can jump into Q&A. I see one. Excuse me. Dallas Bienhoff said, hi, Dallas. It says, hold on.
Oh,
Sorry about that. Dallas says, oh, it appears there was a typo in the title where, oh, I remember what slide this was. Aaron, the title where crater diameter to depth was discussed. You had the wrong number up there. No big deal. Thanks for pointing that out, Dallas.
okay. Yeah, thank you.
And you corrected it while you were talking about it.
Yeah.
So I, while other people are thinking of questions to put in the Q&A, I do have a question. So you you did that really cool work to map regular thickness and you got a number.
Yeah.
Is the assumption of what's below that, what are we assuming is below that? It
Yeah.
completely competent bedrock? Because I mean, the reason I'm asking is a lot of people in this field, in the space resources infrastructure development field, are interested in, well, can we anchor somehow? Is there any competent bedrock nearby? And the general consensus is, well, no.
Yeah, yeah, of course. I mean, so when I say regolith, I mean the fluffiest surface regolith. When I say bedrock, I don't think of competent rock. I think something more competent than this surface layer, which is mega regolith, which are like blocks of rocks, but not the competent intact rock as we would see it, as an outcrop on a highway. Yeah.
Okay, perfect. Okay, now a bunch have popped into the chat, so I'll get to those. Thank you for answering my question.
Mhm.
Nityogopal Goswami asks, how did you know the pressure wave during impact is an input to ISAIL?
Oh, so if I understand correctly, the pressure wave is not an input in ISO. What is the input is the properties of the impactor, like the impactor material. So its density, the velocity of the impact, and then properties of the target. And so ISIL solves a lot of equations and essentially predicts the pressure wave amplitude as it would, evolve through the target.
Perfect. So it's an output of that. Awesome.
Yeah.
Uh, All right, moving on. Dallas Bienhoff asks, can you predict what Richter scale is felt at distance from impacts?
Yeah, that would be awesome. So the kind of seismic moment magnitude scaling is also something that we need to look at. But what we know from the impacts that were detected during Apollo is that like Richter scales are not larger than 4.
Awesome. Thank you, and thanks for the question, Dallas. We could dive into Richter scale, and that's only valid for California. I'm going to jump in. I'm assuming you're using moment magnitudes for these equivalent calculations
Yeah,
of earthquake and moonquake signal.
yeah,
Awesome.
yeah.
Um, okay, sorry to jump in with one of mine there. Sari Nunn says, "Hi Andrea, great talk. Can you say how you define P wave peak amplitude, especially on the moon, where it is an emergent signal?"
Hmm. So, um, what I take out of ICEL is essentially the largest peak that occurs first at my little seismometer. And that's what, I calculate as a P wave peak amplitude. And then from Latam's work, essentially whatever they reported, and I compare it to each other.
Um, Nithyoga Goswami, who asked the question about ISAIL inputs versus outputs earlier,
Mhm.
said, "Thank you. I didn't get it the first time, so
Yeah, I
cheers."
didn't quite explain the methodology well. I
No, you
didn't
did
dive
fine.
into it. Yeah.
Exactly. We never have time in a talk like this. Now, if you guys will excuse me, I forgot to grab the link to the YouTube channel and the AIAA Engage public forum where slides from this webinar series are posted as able. I am grabbing those links now. I'll punch them in the chat because I have access to chat. Attendees do not per AIAA policy. Chat everyone. All right. Here is the link to the AIAA Engage page. You do not need to be an AIAA member, but you do need to make a free account with them to access that. Then for YouTube, where this will be uploaded later, here is the link for that. And if anyone doesn't get these, you can always reach out to contact me. Just wanted to say, get those things out of the way. All right. I don't see anything else in the Q&A. So I guess the question I always like to ask, since we've got just a couple of minutes left, um, what what do you see is the greatest well, let me back up. NASA recently announced that they're going to be making a moon base under the Ignition initiative program. Not quite sure on the right terminology. Apologies to anyone I'm offending with that. But out of this work that you presented, it obviously has fundamental implications for monitoring, hazard assessment, and so on as we do more sustained lunar exploration. In your personal opinion, what's your favorite application of all of this to enabling that sustained presence? Not the most important, but the one you think is the coolest.
Well, obviously, because like a lot of this, applying this to the moon comes from applying the seismic impact-induced seismicity comes from my PhD work. I mean, that's for sure
Yeah.
kind of what I'm excited about to have like newly renowned relevance for my PhD, which was based on Martian impact-induced seismicity because I was part of NASA Insight. Um, but another thing is, I think, what we don't know anything about the regular thickness on the moon. I mean, these are estimates that I show from a method that I used. But as you may be seen in the slides, these are very variable between the methodologies. And the regular thickness will determine how much of the resources we can store within it and what we can use, how much regolith we can actually use for building and stuff. So I'm excited to see that part too.
Oh, absolutely. The operational implications are extensive, and thank you for doing this work. It's cool to actually see the community's been asking for regolith thickness maps kind of thing, and this is a perfect uh introduction and start to that. Oh, I do see Dallas asked another question in here, and it makes very good sense that Dallas is asking a lot of questions for his work. From the most recent impacts, what is the estimated size range and velocity of the impactors?
So the size of the impactors is one, okay. Oh, of the impactors. Okay. Yeah, I see. I see. Let me
Mhm.
just double check. So what I use as a standard impact velocity is 15 kilometers per second. And what is the impactor radius is between 2.6 centimeters to 1 meter in order to form 1 to 50 meter diameter craters. So here is the slide. I kind of rushed through it. So essentially, from knowing the size of the craters, we can use the scaling laws that we have used throughout, time to estimate the impactor radius. So A here is impactor radius, D is crater size, and then using the kind of density, standard density for asteroids and standard impact velocity on the moon, we can get the impact momentum. And these are the ranges of impactor sizes, masses, and impact momentum using this scaling for 1 to 50 meters diameter craters.
It does not take a large object to make a huge crater at those
Yeah,
velocities.
exactly.
That makes
Because
great sense.
kinetic energy is velocity squared. So if you have 15 kilometers per second, square it, that's a huge amount of energy that you deposit from something very small.
Exactly. We're almost at time. Dallas asked one more question. We'll take that and then we'll wrap up. Dallas Bienhoff asks, what about the frequency buckets for size? So I guess like, do we have an understanding, like a frequency distribution of impactor size versus radius?
Uh, Frequency distribution of the current impact flux.
Yes.
Yeah, yeah. Yeah, I mean, we can, it correlates. Yeah,
So,
yeah.
and that those are published, Dallas. I've seen them around. I don't remember where. We can all
And
tag
there
them
is
offline.
discrepancy between size frequency distribution of asteroids and actual craters, but we can
And
discuss that at the next talk.
oh, that's interesting. Yeah,
Between the cometary and the
yeah,
asteroid impact and yeah.
interesting. Correct understanding. Do they match the MMOD distribution frequency? I don't know what MMOD is personally. I should. Uh, I don't know, Dallas. Micrometeorite orbital.
Oh,
Yes, that okay.
yeah.
Go ahead, Andrea.
That is something that I recently started being interested in. And that is something that we don't know much about because it lays between kind of the impacts community and space weathering community. So I feel like maybe having a better conversation with like the space weathering community will give me a better sense for this.
Fair enough. Well, I'll try to get someone from the space weathering community on soon, and we can have that exact discussion.
Yeah.
But for now, we are 1 minute over. I'm sure people have places to be. So Andrea, thank you again for lending your time and sharing all this knowledge with us. This
Yeah.
is really cool work you're doing. So thank you, and thank you everybody for attending. I guess until next month, have a good rest of your April. I will see you all in May. Um, Again, I put links to the AIAA Engage page for the slides and YouTube video link page. So we will feel free to access those and reach out to Andrea or I for any questions. Thank you, everyone. Have a great rest of your Tuesday and a great rest of your week. And thank you again, Andrea. It was awesome.
Thank you. See ya.
Awesome. Bye, everyone.